Uh, how was your lunch? Good. So after lunch, you are very sleepy, right? Because your blood is keep concentrating your stomach to make your exercise in your body. So your blood oxygen and your blood streams are very much slow down. So it's very natural, you know. Yeah, if you eat a lot, I'm sure you have a more contraction for your stomach and have a more sleepy. So if you feel sleepy, you can stand up and then I will ask a lot of questions. You will be very much wake up. Yeah. So feel like you're very sleepy, just stand up. I will ask a question. So make you more comfortable for the class. Okay, so now is time to talk about a little bit more osmosis, concentration, polarization, and then permeate flux to design our process well. So osmotic pressure. So reverse osmosis, cold osmosis, already I explained the detail. So we just have several examples in our body osmosis, even like fruits, like a cherry. You know, when you have a very big cherry, and then if you don't take this fruits, and when you have a raining, so this rainwater will be absorbed by the membrane from your cherry. So the water is keep swallowed, and then cherry will be damaged. So that's the one of the example of the osmotic membrane, even in the skin of your fruits. It's like you have this kind of osmotic pressure. So this is the cherry membrane. Even, you have a coconut. The coconut is a big fruit inside. Water is keep accumulating, and then they are passing through the water inside the coconut, and you have a different taste of the coconut, a little bit sweet, and they are continuously, yeah. So water is even accumulate from the inside, outside, from the membrane. So this osmotic pressure, depending on your dissolved solid, so concentration, polarization. Let's say sodium chloride, 1,000 milligram per liter, 1 gram per liter, which means 0.1%. So 1,000 milligram per liter, 1 gram per liter, 0.1%. So seawater is 35 gram per liter, 35,000 milligram per liter, and 3.5%. So inside the percentage and gram per liter can be converted. So sodium chloride, 0.1% of sodium chloride. So osmotic pressure is 1 bar. And then magnesium sulfate, even sucrose. So you have sugar or glucose. So even this one is dissolved. Whatever dissolved in water, so you have some chemical potential. This will create the osmotic pressure. So osmotic pressure, so one sugar 0.1%, so 1.5. 1.5, in fact, kilopascal. So 100 kilopascal is 1 bar. So 1.5 kilopascal is 0.01 bar. So when you have a same concentration, even sodium chloride, 1 bar, 1,000 milligram per liter. So sugar, 1,000 milligram per liter, it's only 0.01 bar. So they have a different dissolved solid, created a different osmotic pressure. So how we can explain? Like a seawater, 35 gram per liter, 3.5%. Osmotic pressure is 27 bar. So 27 bar means you recover 50% of this seawater. So your concentration increased 3.5% to multiply by 2 times, 7%. So 7% osmotic pressure is around 2 times, 27 bar. So which means you will have a 52 bar pressure of osmotic. So your applied pressure has to be higher than your osmotic pressure. Otherwise, osmotic pressure will be different water desalination. So it's like a forward osmosis, not reverse osmosis. So you have to pressurize more than osmotic pressure so that you will create the reverse osmosis. So we just say reverse osmosis membrane. So RO membrane, the 27 bar we have. So why is it different? Sugar is only 0.01 bar. Sodium chloride, ionide is 1 bar. And how this can be explained as a fundamental theory. So that's what it is 1901, the winner of Nobel Prize. He got the Nobel Prize based on this very very simple osmotic pressure equation. So he mentioned about this is the very famous equation. I'm sure that you already learned from your high school. You know? It's a uh, Bandt equation. He developed how to calculate osmotic pressure. So pi is osmotic pressure is equal to C concentration. R is the ideal gas constant. T is temperature. So if you have a high temperature, you have a high dissolved ion. So you will have a more high osmotic pressure. So this is the proportional to the high osmotic pressure. So concentration, R is the constant, T is the variable depending on your seawater temperature. That's why you have also look at the winter time, summertime, 10 degree, 30 degree. Based on this equation, the high temperature, high osmotic pressure, you need to also pressurize more to produce more water. So it's like osmotic pressure calculation will impact overall reverse osmosis permeate. So how this can be calculated? The C. So look at the seawater. So when you see sodium chloride, these are very straightforward. Only two ions, sodium plus chloride minus. Two ions impact your osmotic pressure. But seawater, as I mentioned, seawater contains more than 100 billion ions inside. So how we can calculate the seawater, yeah, osmotic pressure? It's a very much time consuming, also very difficult to see what is inside. So we can easily predict the sum of the osmotic pressure from the concentration. And the difference is sugar, sugar, it's not ionized. It's like organic, but they are neutral. That's why if it's not ionized, you don't create the osmotic pressure. For sodium plus chloride minus, you have two ions. Yep. So your two ions concentration is 1,000 milligram per liter, 1,000 milligram per liter. In fact, they are contributing as a 2-ion osmotic pressure. Also, if you have a different compound, let's say calcium chloride, calcium is 1, chloride, CaCl2, chloride 2. So you have 3 ions inside your uh, water. So this is 3 times. So when you have a more ionized form, you have to multiply. Sodium chloride, 2 ions, multiply by 2. Calcium chloride, 3 ions, multiply by 3. And then depending on the how many ions dissolved inside, you have to multiply. That's what it is. Sodium chloride, ionized, osmotic pressure is very high. And this sugar is no ionized, it's more dissolved as organic neutral charge. So you don't create the osmotic pressure. So that's the difference you can calculate. But the seawater, too many ionized form, it's very difficult to calculate. So we just make a very rough total dissolved solid concentration and then calculate around 27 bar pressure depending on the your concentration of total dissolved solid. So that's the how we utilize the osmotic pressure using this Van Hoff equation, and then you can calculate your RO design. So this is the osmotic pressure, how much we can create the 28 bar and then 50% recovery ratio. So this is the energy consumption, 50%. And concentration polarization. This is the another important concept. So what happens is the water is flowing, then concentration is continuously increased, feed water, because they desalinated water. And then concentration is continuously accumulate, and you have a more polarization impact. So you have a polarization because of high pressure. You have a high concentration on the membrane surface rather than bulk channel flow. So your concentration of on the membrane surface, concentration of your channel different. So you have a higher concentration on the surface of membrane, and then this is concentration polarization. The osmotic pressure will change on the top because you keep pressurized the 70 bar, and then ion is keep trying to pass through the membrane because water is keep passing through. So they are keep accumulating on the membrane surface. So real osmotic pressure is different from bulk solution, membrane surface, and membrane permeate. So that's the exactly we just thinking about concentration, polarization, what's the exactly osmotic pressure on the surface of your ion. And this is very challenging because your feed side is keep changing concentration, your concentration polarization on the top of membrane keep accumulating. That's the reason why we have to think about carefully how we can calculate this osmotic pressure, also how we can release this concentration polarization because they are continuously accumulating. And unless you release the pressure, they will continue to create the concentration polarization. So we need to design the second stage, the little bit mixture of your feed side, then concentration will be mixed, and then go for the next stage. We'll have a less concentration polarization. That's the how they design for this concentration polarization. We are recording now? Yes. So what's the element? So you can design element. So this is the 40-40 element. We just say 40-40. 40-40 means 40 inch. 40 inch means 1 meter. This is 1 meter, 40 inch. And then 4 inch is the 10 centimeter of diameter. So 40-40 means 1 meter, 10 centimeter of the one element you can install. And, okay, sorry, 80, 40, 80 inch. So BW 40 is 1 inch is 2.54 centimeter. And then 40 inch is almost half size. So 50 centimeter. So 40-40. And you have a SWRO 25 diameter, 2.5 inch and 40. Length is 50 centimeter. And this one is you can select which kind of size and length, and it depending on the membrane surface. So you can calculate how many elements you need to design your overall water capacity. That's the reason why we need to have a 40 inch, 40 inch length for diameter in the initial flow, and then the last two digits, 40 inches is the length of your element. And SW is the BW is a brackish water, SW is the seawater. So they are selling different module configuration because the BWRO is more of a wastewater. So brackish water, wastewater desalination for RO, so they have a more contaminant. So they have a larger channel. And the seawater is less contaminant, but the salt is more. So they have a high pressure, so they have a less channel thickness. So that's how they design different size, different configuration, SW, BW, reverse osmosis, and they have a compatibility. So we have around 100 RO membrane company in the world. So if they design different membrane, like some company 20, 30 inch, some company 10 to 20 inch. So you cannot buy other company membrane element. It's very difficult. So they have a standard. Okay, length is almost 40 or 80. The diameter, you have a 40, and you have also 25 and different 80. So they can select which kind of, yeah. But every company has to design within this classification. So they cannot design because they cannot utilize in other desalination because this is consumable. After 1 year, 2 years, you can continue to replace. So in this case, if your size is different, so you cannot utilize other company. So they have their own standard, and they utilize compatibility of the pressure vessel and caps and size. So they have a little bit of lack of diversity. So only this kind of size currently utilized for desalination. And then let's see how this element is manufactured. So if you see this manufacturing process, you will have a better idea how we can connect this one as a membrane element.
Philotech Corporation, a subsidiary of the Dow Chemical Company, is the world's leading manufacturer of reverse osmosis and nanofiltration membranes. Our products are used in a wide variety of industrial, municipal, residential, and commercial applications, helping Dow achieve its mission of improving what is most important in life, the human element. Our cutting-edge manufacturing technology improves the performance and quality of our membranes and provides the scale and infrastructure to serve the rapidly growing demand for RO and NF membranes. Providing high-quality membrane products starts with quality raw materials from ISO-certified suppliers. FT30 thin-film composite membrane, invented by FilmTech nearly 3 decades ago, is the genesis of today's industry standard. With each new generation of manufacturing equipment, the quality of FilmTech membranes is continuously improved through advanced process automation and control, from handling polyester-based material through casting the microporous polysulfone support to the complex polymerization reaction that creates the polyamide membrane layer. Design innovations allow us to use advanced membrane recipes that improve membrane performance and consistency. Dozens of critical variables are controlled and inline quality checks are performed to produce consistent, defect-free membrane without patching, and giving FilmTech membrane the widest pH cleaning range in the industry. A spiral wound membrane element can be fabricated manually or automatically. Dow uses custom-designed precision rolling equipment to automatically fabricate FilmTech elements because it allows for better, more consistent element performance. Sophisticated robotics for lead construction and assembly ensure that every element is precisely built without membrane damage that often occurs during manual handling. Automation enables construction of more shorter leads compared to manual rolling, resulting in a more efficient product that is less prone to fouling. Precise computer-controlled glue lines ensure the highest active area in the industry with guaranteed accuracy and minimize leaks, which can result in poor permeate quality. FilmTech elements are optimized to have the highest active area combined with the thickest feed spacer in the industry, offering several operating benefits, including improved cleanability, lower pressure drop, increased durability, and the ability to handle more challenging feed waters. A unique barcode allows continuous tracking of each element. Online quality checks for scroll integrity and dimensions and an inline vacuum test are performed on every element to ensure mechanical integrity. Any elements failing preset measurements are discarded. End caps are welded to the product water tube in a process that improves element strength, and a quality test ensures weld integrity. Our automated fiberglass process ensures exact and uniform fiberglass application within controlled dimensional tolerances. To validate final element performance, FilmTech uses both a traditional 20-minute performance test and a groundbreaking pulse integrity test, which has the unique ability to detect and diagnose mechanical defects. Tests are computer controlled, and elements not meeting defined test ranges are discarded. Custom designed packaging equipment combined with precision injected preservative ensure protection for elements during storage and transportation and easy handling. Prior to shipment, product for each customer order is scanned for traceability and to validate all previous quality checks. Quality is built into every FilmTech element, from the management of raw materials to final shipment. Every element undergoes multiple inline quality measurements, and additional parameters are measured based on defined sampling plans. Our technology enables a robust, consistent, defect-free membrane with the industry's widest pH cleaning range. Automated precision fabrication enables elements with maximum guaranteed active area, the industry's widest feed spacer, shorter membrane leaves, consistent high-integrity construction, and ILEC interlocking end caps. Collectively, these features enable consistent, reliable performance of RO systems with reduced system capital and operating costs. With the infrastructure to meet the rapidly growing demands of the market and the technology framework for integrating future innovations, Dow continues to lead the industry in reverse osmosis performance and value enhancement. Our goal is to offer the best membranes to enable the highest quality water at the lowest total cost. Innovation, automation, quality, film tech.
So usually they automate it. In fact, they don't really produce by people. This is the little bit reduced size. So they have a 10 centimeter diameter and 1 meter. It's a very typical size of seawater desalination. Then they put the membrane spacer, backspacer, then continuously roll. Then maximize the membrane surface area. Also, the pressure is very high, like 70 bar. So if you don't have a very compact, this module will be burst easily. Also, membrane can be easily damaged. So they generate this kind of a spiral round module design and then produce the good quality of membrane system. So that's how we create the one element. It's $500. People just to buy one element can produce a lot of water. So this is the pressure vessel. So you can see the element is this one inside. You're putting the element, one element. So you have a connector. Then your pure water is coming out from here. And you connect again, 2 element, 3 element, 4 element, 6 element, 7 element. So you need to pressurize 70 bar. So you need a very strong pressure vessel. So inside you have a element outside pressure vessel, which can tolerate 70, 80, 100 bar pressure of your membrane. So pressure vessel require this kind of a strong material. So they have like a fiberglass or stainless to tolerate the overall high pressure. So you can design how many pressure vessels we need, how many elements we need. So that's another your question for your assignment. The pressure vessel, we need one pressure vessel. We can include 7. It's a 7 or 8 or 6 are the typical way of the element number. So you can design seawater for your assignment, maybe seven elements in one pressure vessel, which will give a good design. And this is the pressure vessel typically have a different flux distribution, pressure distribution. So you have your feed water, seawater coming through this way, and then continue to increase your feed water concentration of salt, and pressure is different from initial stage and last stage. Also, your flux accordingly will change the initial element. So they have a lot of flux. At the last, they have less flux. Yeah. So this is the flux distribution, pressure distribution. You need to also calculate as a whole pressure vessel design rather than one single element of your membrane flux, and feed water. So we need to consider this one. Also concentration for the salinity in the permeate. So first element, last element, 8 element. So your permeate is 150 milligram per liter. At the last one is almost 450. So they are increasing a lot. So you have to look at also overall concentration change from element 1 2, 3, 4, 5, 6, they combine together and then mixture. So you have to see carefully also pressure, permeate flux fraction. So you can see 25% more higher water flux and 10% element 5, and you have a last element, and this is 5%. So this will give a better way of your water flux. So you have to also look at the different element has even though one pressure vessel, they have a different water flux. So you have to also calculate each element, how they behave. So that's the overall design and spiral round operating condition from what we know. And first element, last element, and design implication range, you have to see carefully. And this is the spiral round behavior of the stage. So pressure profile. So you have a first, second, third. The first stage, second stage, third stage. So one is the one pressure vessel, second pressure vessel, third pressure vessel. Then this is the second stage, and then you have a different. So concentration polarization, when they pass through the first stage, your water is mixed again. And then concentration polarization, your salt concentration is consistent. And then enter to the second stage, and you have another concentration polarization, and then mix again, and then go last stage. So osmotic pressure, driving force, applied pressure is continuously changed. It's not exactly, you have one high pressure pump. So every stage, every element will change a little by little, your pressure change. So how we can make sure that this kind of a pressure change, osmotic pressure change, and then finally you can calculate all the necessary design. So this is the pressure pump. Sometimes you can put the boost pump because you apply 70 bar pressure, first stage, and second stage, you want to have a same pressure, 70 bar, because you have a pressure drop, your pressure decrease, but I want to make the same pressure at the initial stage, or you want to increase. So you can have a boost pump at the second stage and third stage. You can control each stage to make a consistent pressure to avoid any pressure drop at the last stage. So this is the, if you see the stage 1, 2, 3, and flow rate decrease this way, and this way. And then flux, it's continuously decrease because feed water concentration polarization, your TDS osmotic pressure increase. So your flux is continuously decreased, and feed side concentration is continuously increased. So you have a different behavior, even same element, same pressure, but depending on the how you progress, you will have a different behavior of the feed flow rate and feed side concentration, water flow, water pressure. So how we can calculate this detail? It's very challenging, right? So each element, each pressure vessel, each concentration polarization, each flow rate. Also, flow rate is one of the frequent error for your design. So if you don't give enough flow rate, at the last stage, you don't have enough water. So you will get the error message for your simulation of the software. So flow rate has to be also very well flow. Permeate at the same time, your permeate flowing very good design. And then pressure has to apply carefully. That's why your design is no error rather than you have to owning sign. So luckily, whenever you have a report in the software, you can say, okay, your flow rate is too high, too low. So you can go back and then change a little bit of your flow rate. Also, or you have too much high concentration of your feed water at the last stage. Then you have to also change your recovery, how much you recover. And you have to think about the design. Also, when you operate long time, so you have a mostly colloidal organic fouling at the beginning stage, and then scaling is at the last stage. And this is the spiral. Excessive differential pressure can cause structural damage, membrane telescoping, and because the pressure is too high, so you have a little bit of membrane telescoping phenomena. So in this case, yeah, we have to replace this membrane. And this is the design, how we can make a good design of overall our process. So let's look at the more specific design terms. So this is feed side, the flow rate, Q, quantity and concentration. So you have a retentate, reject, concentrate, brine is here. So how much is coming out? And permeate is QP, CP. So we can have a very simple way of the feed, permeate, and reject. So this will give a membrane element. So we can have some of the recirculation way of the process. And this is we just say average permeate flux can be calculated. So feed is passing, and the average permeate flux is in terms of LMH. So QP, how much permeate is produced, and then membrane area per hours. So 1 hour, how much water is passing through your element, and then you have divided by the membrane area. So this is the salt passage. The feed go, and then salt is passing through. So how much salt is passed through? Because our membrane is not perfect. So you already look at the video. So some of the defects are existing in our membrane. So this defect can pass through your salt. So your concentration still little bit of salt is passing through. So salt passage is the CP to CF times 100. So you will get how much rejection will be achieved from your membranes. Also, each membrane is different because some of the salt too high. So you need to have a very high salt rejection membrane. Like a wastewater reuse, there are not much salt. So you can have a little bit low rejection reverse osmosis. So even the reverse osmosis membrane, it's not exactly same RO membrane. They have a little bit loose RO, tight RO, compact RO, high rejection RO, high flux RO. So if you have a larger pore, you have more flux. If you have a small pore, you have a high rejection but low flux. So depending on your water quality, you can decide which membrane is the best choice of our. So seawater is luckily a little bit consistent water quality. So you can select how we can provide a good quality of water and membrane module. So you can think about what's the best way to select your seawater desalination. So salt rejection, this is a recovery rate. QP, QF times 100. So 50% of the recovery. And we have a membrane element. So we have a pressure housing and the pressure vessel. Each element can be connected with the O-ring. And this will give a permeate side and then concentrate side. So you can get the both side, both channel, and then continuously combining this. So let's have a little bit of practicing because if you use the software, yeah, you don't understand what's the exactly recovery happening inside. So one pressure vessel, you have a 7 element, 1, 2, 3, 4, 5. So you have a 1 meter, 1 meter, 1 meter element inside one pressure vessel. So 7 elements, 7 meters. You have 7 meter, one pressure vessel. And then let's see each element, how much recovery we can get. So our target is the CO2 desalination, let's say 40%. We want to achieve 40% of the last water recovery. And see, okay, feed side flow rate is 8 cubic meter per hour. And we pass through the one element. So we get the permeate 1 cubic meter per hour. And we can take concentrate brine is 7. So 7 divided by 8. So we get one element, 12.5% recovery. Then let's think about second element. Second element, we go through, first one was 12.5%. Second one is, will be reduced because they decrease the flow rate, 7. We start from 7, and then this is initially they have 12.5% of the recovery, so which means 0.012 times 1 minus 0.012, which means second element will recover 10.9%. Third one will decrease again around 8%. Then next one was decrease again. So continuously each recovery decrease. So we like to get 40% of the recovery from A to 3. 3 permeate, and then 6, 4, 3, and 6. 3, 5, 5. 3, 5. 5 we can take, and then this is equivalent to 40% of the recovery. So that each element you design 12.5%, next one 10.9%, next one almost 8%, 10%. All together, final your return pay is your 40% recovery, 5 kilometers per hour, and permeate is 3 kilometers per hour. That's why you design for 40%. And this one is more complicated when you design second stage. So this is first stage, only one pressure vessel. But this is not enough to achieve 40% of the recovery. So you need to connect another pressure vessel at the behind, another one, and then you have to calculate 40% at the end of your permeate. So which means 40% is not enough for the one pressure vessel, 7 elements. So you connect another pressure vessel, and then they keep decreasing the recovery rate. Finally, you will achieve that. Because seawater, because of the concentration polarization, you cannot achieve one pressure vessel with 40%, 45% of the recovery. So you have to calculate first stage, second stage, and then your recovery, each element will be different. So that's the how we have to think about your overall recovery rate. And this is the single stage pass system, two stage RO system, two pass. So in your assignment, you have a boron concentration issue. So when you input your boron concentration from your scenario given value, you will have a very difficult to pass your boron less than 0.3 milligram per liter using first pass. So first pass, second pass, first stage, second stage. So your design has to utilize this second stage and second pass to achieve your final water product and your final recovery. So stage is related to your recovery. Pass, first pass, second pass, relate to your final permeate water quality. So in your assignment, you have to design both way. Second stage, second pass. That's why it'll be a good design of your overall process. So let's see the detailed concept of stage. So first stage. So we have four different pressure vessels. And then second stage, the retentate, the brine is moving to second stage to achieve the higher recovery rate. And then you can get the 40% of 45% recovery. If you go stage 3, you can achieve more high recovery, 50%. But it's not effective way of design. So we just go for seawater desalination, first and second stage, and you have a better idea to get the final your recovery ratio. So stage can impact your overall recovery ratio. So this is the example. So let's say your feed water is 1,000 milligram per liter. Yep. And flow rate is 840 cubic meter per hour. So this water is passing through your first stage. So they have a concentration permeate. The feed side decreased to 12 milligram per liter. Then flow rate is around 468. It's almost 45% of the recovery. And then you can see the next step, second stage, you further increase your permeate total dissolved solid 60 milligram per liter. Flow rate is a little bit less. So your third stage, because of your feed water concentrate, so increase the 240 and 51 LMA. So we got the final concentrate 7,400 milligram per liter and 125, which means the recovery is 85%. So you pass through first stage, second stage, third stage, you achieve 85% of your recovery. And you can see the permeate. You collect permeate here, 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 and then combine together. So from 1,100 to 40 milligram per liter, then your flow rate is 750. So each stage increase your concentration, decrease the flow rate of the permeate, and then increase the overall water flow recovery. So we just say 7, 4, 2 array. So when you increase your overall recovery of your water, you have to continue like a 7:2 ratio or 4:2 ratio or 6:3 ratio. So you have to also design your CO2 desalination different way of your array system. So your array can be impact the recovery. Also, you have a second pass, first pass. So one of the assignment question is about how to achieve boron concentration less than zero point 0.3 milligram per liter. So when you design only first pass, yeah, this is not good enough to achieve the zero point 0.3 milligram per liter of boron. So you can go through your permeate another arrow to increase your overall rejection of salt. Yeah. As I mentioned, arrow membrane is not perfect. So there are many defects. Will pass through some ion, or some of ion was very much easily pass through. So you go through another barrier as a second pass. So your permeate will be increasing the overall quality of your water. So you have a better way of the design for the second pass. So you have to utilize the second pass design to achieve your boron concentration less than 0.3 milligram per liter. Energy. Already I mentioned about energy. Energy is the most problem for water desalination, right? So how energy distribute? So you can get more idea about how we can have a saving of this energy consumption of the water desalination. So look at the pre-treatment intake. So when you pumping your water from seawater, it's only simple pump, so 0.2 kilowatt hour per cubic meter. So 5% of your energy consumption in desalination plant. And pre-treatment, it could be ultrafiltration is a little bit high, and this is the dual media or multimedia filtration, like a center filtration. The energy consumption is 0.4 kilowatt per hour. Cubic meters, so 10%. The arrow is there. Okay, next step is the arrow. So most because you have a very high pressure pump to overcome your osmotic pressure. So you need to utilize 74% of overall your energy consumption, 2.8 kilowatt hour per cubic meter, and post-treatment discharge is only 0.3 kilowatt hour per cubic meter. And the other facility, just general chemical or monitoring 0.2. So RO is 72%. So if we could reduce the RO energy consumption, we can save a lot of money. How much money we can save? Let's figure it out. You can calculate because light bulb. So how much energy do we need? So let's see energy calculation. RO, pump. So mostly energy consumption is a high pressure pump. Yeah. So why this high pressure pump is very much required for this overall energy. So like a seawater flow rate, example of 100 cubic meter per hour. Apply pressure, we need a 75 bar pressure. And then reverse osmosis recovery, let's say 40%. Then permeate flow is 40. So let's see how we calculate overall the energy consumption So you can see this is the pilot, real data of your calculation, specific energy. You operate this system, then you need a 300 kilowatt hour energy consumption, and then you produce the 40 cubic meter per hour. So we get 7.5 kilowatt hour per cubic meter. So when you utilize energy recovery, so what's the energy recovery? So you pressurize 75 bar, and then at the end of your process, if you don't observe the energy, it's all wasted. So this pressure can be exchanged. So if you use the turbine energy recovery, so you can save the 30 to 40%, 4.4 kilowatt hour. Pressure exchanger, 140 kilowatt hour. So you have a 3.5 kilowatt hour per cubic meter when you use energy recovery. Even this is the overall pilot data, but okay, you need a theoretical calculation. What's the energy consumption of this process? So let's say 70 bar, 3 cubic meter per second, pump efficiency 0.8. So you have a feed farm, is energy consumption is a flow rate, and then you have a pressure and pump efficiency. So 3 cubic meter per second flow rate, 70 bar pressure, and pump efficiency 0.8. So you need to have a 26, 250 kilowatt cubic meter per hour. So you can convert this overall energy consumption, and then you will get this final data, 7.28 kilowatt hour per cubic meter. So your pump energy consumption can be also theoretically calculated. So high pressure pump requires a lot of energy to utilize for your body. So how much you pay for 1 kilowatt hour? So when you produce your 100 cubic meter per hour pressure, you need a power consumption 300 kilowatt hour. So what's the 1 kilowatt hour energy price? 1 kilowatt hour, how much you pay for your energy bill? Not, you don't have to, every year. How much you pay for energy bill? Because now a lot of people are worried about energy bill, right? Energy costs in your home. So you don't worry about energy bill. Right? You don't care about energy bill. You don't pay. I don't think my bill is included. Okay, you're right. Included. Who pay? Who pay for energy? You pay. How much you pay for? Huh? You can see it. Over 12. How many people? Is it 4 people? Is it like is it quarterly? It's for 170 things. So it's one day. So this is the house or apartment? It's house. House. Yeah. So she live in house. Like a typical full family, yeah, 4 members. Yeah. Then pay every 3 months $412. Every month is almost you should pay how much you should pay? 400, let's say $140. Yeah. $140, which means do you know how much energy you use for this one? Yeah. So that's what it is. Okay. So let's say what she's paying for let's have a little bit of specific calculation. What I like to do is, uh, so she pay 400. It's okay to cover this. So every 3 months, so she pay around 173 per month. So let's say 1 month is, let's say, roughly 30 days. Yep. So every day you pay $4.5. So what's the energy consumption? So how much you pay for, let's say, we can have how much for 1 kilowatt hour in Sydney? Compare electricity. Okay. And this is not the, let's put into the Google. So let's say, in fact, 27 cents, maybe some council discounted ratio, maybe public, facility, and to 47%, maybe some of the other. So let's say average 30, 35, let's say 35 cents, 35 cents, you spend 4.7 kilowatt hour, so multiply by $0.37. So in fact, you pay every day $1.7 for her energy. So which 1.69 kilowatt. Yeah, kilowatt, sorry, kilowatt. So she utilized in her house 1.69 kilowatt per day. Yeah, is it right? 1.69. So mostly beige one, like it's a very modest way of utilization. So guess, so what is desalination? 1 cubic meter. Desalination water requires 4 kilowatt hour energy. So 4 kilowatt hour point $35. How much? So almost $1.23, right? So when you produce desalination water, you need 4 kilowatt hour. Should you need at home aggregate 1.6 kilowatt hours. So even, 1 cubic meter of desalinated water is very expensive because it's more than one household, 1 day consumption. It's almost triple times, right? Triple time. We have to spend for the seawater desalination. That's exactly we have to save because otherwise a lot of money because the seawater desalination in Sydney is 250,000 cubic meters. So multiply by, so let's say Sydney desalination plant produce 25,000 cubic meter per day. Energy consumption is 4 kilowatt hour per cubic meter. And then 1 kilowatt hour is $0.35. Is it? Why this? Why this way? It can't be like this, eh? 25555. This is the multiply by you have 4 kilowatt hour per cubic meter. 4. Multiply by, oops, something is wrong. Let's clear. Okay. So we have a 250 cubic meter per day from Sydney desal plant. Then they require 1 cubic meter, 4 kilowatt hour. So multiply by 4. So it's 1 million. And then we need to multiply by $0.35. So every day, Sydney desal plant spend only energy, only energy consumption, right? Produce your work for that. That's exactly what's used. Big money. Also, only energy. It's only energy. It's not relevant to capital. It's not relevant to any of replacement, consumable. Only energy produced daily, desalinate water, 150 kilograms a day. When you multiply by 365, 365 days. Yeah? How much can you guess? So 1 year. So you can multiply by this one again, 365 days. Every year, $127 million, right? So desalination, only energy consumption is $127 billion you have to spend for the energy cost only. So it's very big money. So that we have to make sure how to reduce the overall energy cost will be the very much saving we can do. So this is the general calculation we have tried now. So this 1 kilowatt. So 1 kilowatt, 0.35 cents, dollars, 3 points dollars. It can turn on your light bulb almost 1 hour, and this is the 100 light bulb. You can just turn on like this kind of, so almost the whole building of the light, 1 kilowatt, we can utilize. Yeah. So she's using 1.67 kilowatt per day. Yeah. So you can have this kind of 1 kilowatt is not really small. Yeah, it's a very much typical way of energy consume. But this 1 kilowatt itself, it's not that much small energy consumption. You can think about it. So that's the energy. A lot of people are talking about energy crisis, energy issue, energy saving, energy bill, so energy supply, oil, natural gas, hydrogen, solar, wind, fuel cell, battery, because they really put a lot of money in this sector. Yeah. That's we have to think about how we can make sure. Also, to save this energy, as we discussed, pressure exchanger was developed. And then we saved more than 60%, 70% 80% energy consumption in hour. So let's see how this energy recovery save it's almost every year. You remember how much every day 350. So we save half 1.25 125 $100,000 for Sydney desalination plant. So let's see how this energy recovery save the energy pressure cost, and then you will get some idea. Oops. Oh, this energy.
It's crazy that a planet covered in water is running out of the stuff. That's why this is so important.
But what you're looking at here could be one of the most significant engineering breakthroughs you'll see in your lifetime. Predicted that by 2025, demand for fresh water will exceed supply by more than 50%, leaving a third of the world's population without ready access to fresh water. But we don't call ourselves the blue planet for nothing. Our vast expanses of sea may well be our saviour. It's a process called reverse osmosis, where huge amounts of energy are needed to pump seawater through fine membranes which filter out all the dissolved salt. But as you're about to see, a simple invention has revolutionised desalination, and those high operating costs are no longer a major problem. While modern desalination plants are far more efficient than they were 20 years ago, they still use a whole lot of energy, most of which is wasted. On average, it takes 3 glasses of seawater to produce just 1 glass of drinking water, but you're still paying for the energy that it takes to process all 3. And that, ladies and gentlemen, has been desalination's Achilles heel. Despite their best efforts, scientists have not been able to radically improve that production ratio of seawater to drinking water. So they began investigating ways of harnessing the pressure energy of the reject seawater and using it to help power the whole operation. Californian company Energy Recovery Incorporated finally cracked the problem with a device called the PX pressure exchanger, which cut energy costs by a massive 60%.
So what the pressure exchanger does is it recovers the energy in that waste stream at almost 100% efficiency. It operates at 97% efficiency, which in engineering terms is extremely efficient.
John McHugh heads up the Affordable Desalination Collaboration, a US Navy joint project with the Bureau of Reclamation. For more than a year now, they've been testing and evaluating the latest desalination technologies, including the pressure exchanger.
With old desalination systems, you used to have to pump 100 gallons a minute to get 40. With the new desalination systems and this pressure exchanger technology, you pump 40 gallons a minute and you get 40 gallons a minute. It's amazing.
Yes, it really is that amazing. Just a ceramic cylinder capped at either end by fixed propeller-like end ducts, and all precision fitted inside a tubular housing. The pressure exchanger is effectively cutting running costs by more than half. And that's great news for cities like Los Angeles. So what does this mean for the future of the world's freshwater supplies? Well, in the city of Perth on the west coast of Australia, it means securing the future. It's about to become the first desalination plant. The latest desalination technology, including the energy-saving pressure exchanger. The $350 million desalination plant will be finished in time for summer next year, guaranteeing regular water supplies for the next 30 years. Back where the technology was invented, California, there are 6 new pressure exchange plants in the pipeline. Every day, the need for fresh water is challenging nature's capacity to produce it. So what you're looking at here could be one of the most significant engineering breakthroughs you'll see in your lifetime.
Do you understand what's how this works? Yeah. Can you explain how this works to me? Yeah. I think this. Yeah, this is the how it works. This is better.
Working on team, you probably know this moment when
It's Rachel from work. She says the Wi-Fi isn't working.
I think this is more clear.
the
For you?
PX captures energy that would otherwise be wasted, reducing a membrane-based system's high-pressure pump flow requirements. Not only does it save electricity, it also cuts high-pressure pump size requirements, producing further savings. Now let's explore the engineering behind this innovation. Simply yet elegantly designed, the PX high-pressure housing contains a ceramic rotor. The only moving part in the entire device surrounding the rotor are a sleeve and two end covers. These ceramic components fit snugly around the rotor to form a tight fluid seal. Water in the narrow gap around the rotor acts as a hydrodynamic bearing, requiring no external lubrication. High-pressure reject concentrate from a reverse osmosis plant's membranes flows into the PX. Low-pressure feed water simultaneously enters the PX and fills the rotor where it is exposed briefly to the reject concentrate. Energy from the hydraulic pressure is then transferred directly from the concentrate to the feed water inside the rotor. This pressurized feed water now goes back into the system and joins the stream from the high-pressure pump. Any remaining concentrate exits the rotor at a low pressure and is then pushed out by fresh water. The rotor ducts charge and discharge as the pressure transfer process repeats itself.
Okay, everybody
Since
understands?
the
Because this is ceramic, so you have a rotation. This ceramic has some hole. You have a arrow. We can take high pressure 60 bar coming after membrane rating, coming to this side. So just the high pressure reject coming this way. And then the other side is seawater feed water, a very low pressure, and then seawater coming. Because of this, two pressure is very different, 16 almost 1. So because of pressure inside, there is a ceramic rotator. So it's because of pressure, it keeps rotating very quickly. They have a hole here. So water, if they have pressure, less pressure, high pressure, less pressure. So this guy have a hole, one hole is going this way, and then when you rotate, and then you pressurize. So your pressure in high push through in the hole of the inside the ceramic. So it go inside this ceramic here, and then move to there, and this pressure push, and they have high pressure, the low pressure push it to retentate. The pressure is observed here, and then high pressure getting out to your feed reverse osmosis. So it's very quickly ceramic rotate. The pressure high, low, high, low, high, low, high, low. Water is coming and out. This feed water coming and out. So continuously they are pressurized of the pressure exchange. And then you can say, rather than high pressure pump, so you can observe from the little tank, and then apply to your feed arrow, high pressure. So that's the how they develop and now it's there. Small and recovery device like that. This is the pressure exchanger. The same as the heat exchanger. So heat is relatively simpler. You go hot water, you come cold water. They observe the heat hot and cold. They go into the heat side again, and then coming back. And you have the heat exchanger is the same like that. Simple way of the heat exchanger is a pressure exchanger. Also, you can observe the sum of the pressure to utilize your feed pump. And then you can apply for boost pump to add a little bit more pressure to operate the reverse osmosis. So that's how they developed the pressure exchanger, and then it can save energy cost. This save every day Sydney desalination plant more than $300,000 every day. So only this small recovery. So only Sydney desal plant. But when you consider in the world how many desalination plants we have, more than 20,000 desalination plants in every world. So how much they save the energy cost because of this small ceramic pressure exchanger? Maybe million, billion every day. They save a lot of energy cost. So that's how they have utilized saving the seawater desalination energy consumption. Yeah. What they touch. So they recently do, but it doesn't really over. Because it doesn't like that. That's the one question. But it does touch. It's like a very quickly move. So you have a very strong rotation. So your touch time is just less than 1% overall your quality. So it's true. If they touch each other, then it's like a moving to this way. But it doesn't over each side. So that's why some people develop, they don't want to touch. They put some like barrier, so they don't want to let them touch. And the only pressure is so that's the next generation of pressure exchanger. So this is the basic operation of pressure exchange. So simple idea. It's like this. Help a lot for the energy consumption, save a lot of cost. So you can think about yourself also how to save the overall energy cost in desalination. Now we are to 3 o'clock. Okay. So, okay, we can finish this one up to here and have a break. So this is the Sydney desal plant information. So you can refer to this one to design your little bit specific assignment 3 design. Because in the question is very simple. How many banks, how many train, how many element, how many pressure buffer, what's the rejection, show your wave software design, yeah, capture. But this is the example of a real desalination plant in Australia. So you can see what's the feed driver, product level, temperature, capacity, was R configuration, partial 2-part, advanced split pass, SP, split pass, then partial 2-part, and then split pass, and they have a two stage. Some of them did not mention about 2 stage or 2.5 stage or third stage to recover your high rate, and then recovery 45%. This is the first pass. Second pass is a BWR, 90% recovery, and you have a different R recovery. First part Second part, BWR, also energy recovery device, pressure exchanger PX, or DWEER. DWEER means dual wall exchanger energy recovery. So it's the concept is the same. You push high pressure, low pressure, then moving again this way. And dual is the little bit different system configuration they have, but the general concept is same. They observe the pressure. So some of the plant in Sydney water, they utilize dual wall exchanger water recovery device. Some of the plant, as you watch the video, the post desalination plant, it's a pressure exchanger energy recovery device. Also, they have a energy consumption, how much energy they spend for each desalination plant, 3.4, 3.9, 4.2 in Melbourne desalination plant, and then reverse osmosis specifically 2.4, 2.9, 2.9. So that's how the desalination plant is currently operating. So you have also basic concept, process, then what kind of staging, water quality, energy consumption, energy recovery device, RO configuration. So it can be also utilized for your assignment 3 to make a little bit more detailed discussion for your report and your design parameters. You can also consider from this Australian desalination plant. So after 15 minutes break, we can have a last session around, maybe we can come back 3:20, 20 minutes, and we can have a last class of the brine mining. So this is also relevant to your brine related management in your assignment report, how you can make a good design of the brine. So we will have a brine mining lectures and then finish the today class, and tomorrow we will go for the wave software designing, computer room. So 9 o'clock you can come back to the tomorrow computer class. Okay, so let's have a 20-minute break and come back. Thank you.